work in a physical sense involves two things. It involves both a force and some sort of displacement or distance covered by an object. If you have those two things involved in a situation, then work is being done. Work is a little trickier than that though. Let's say we have an object here and we're pushing down on it with some applied force. So there's our applied force, and we're applying that force at some angle and we're pushing down on it. Well, the object's displacement is this direction, right? So its distance, it's moving that way. However, my force is being applied in a different direction. So not all of my force is actually going into making this object move this direction. And so we want to pick off, when we're talking about work, just the part of the force that is causing it to move in the direction of its displacement. So to do that, we just use a little bit of trig, and we say that work is equal to force times distance, so that would be kind of our general formula, times the cosine of the angle between those two things. So the cosine of this angle. And that, you can see, cosine would pick off this horizontal component of that force that matches the horizontal direction of that distance, or that displacement. So work is force times distance times the cosine of the angle between those two things. Unit-wise, work is measured in joules, right? A Newton meter maybe, newtons times meters, or kilograms meters squared per second squared would be another way to think about that. So work, and as we'll see later, energy is measured in joules. I'm going to talk for just a minute about the idea of a system. Systems are going to be really big for us from now on, so we want to make sure we have a pretty clear idea of it. So let's say again we have the floor and the box, and we're applying some sort of force on it. Okay, and then it's going to move and do what it needs to do. When we talk about a system is sort of the thing that we're focused on, the particle or set of particles or object or set of objects that we're concerned about within a problem. In this particular problem, we could define our system, we put a little box around it, as being our box, and that our box is in contact with that particular surface. What applies this force out here really has no bearing on that problem, so we're not going to consider it a part of our system. Right? Yes, it's changing the motion of this box and things, but where it comes from, what is applying this force, really doesn't matter. It's just a force pushing this way. So we're going to define our system in here, and so anything that's internal in the system is going to be some type of energy, and anything coming out of the system and pushing in, or anything leaving our system, is work. So that's where work is really important, is because work is our way of transferring energy sort of between the system and its surroundings. So inside the box would be the system, outside the box would be the surroundings, and work is our way of going back and forth between the two. So let's look at work one more time, and let's make it a very simple case where our force and our distance are in the same direction. Now if that's the case, the angle between them is 0 degrees, and cosine of 0 is just 1, so it's just force times distance. Well, work is also, or force is also mass times acceleration, so mass times acceleration times distance. And then we can go back to an old equation of ours, say v squared equals v naught squared plus 2a delta x, and I know we're reaching real far back here. Well, delta x is kind of the same thing as d, so we'll just call that d, right? It's a displacement. And so let's solve for acceleration. And we get acceleration is equal to v squared minus v naught squared over 2 times d. And then we're going to take this expression and we're going to throw it in here for a. So we end up with work equals m times v squared minus v naught squared over 2d times d. D's cancel out, and we get work equals, if we pull some things out here, 1/2 mv squared minus 1/2 mv naught squared. Well, this quantity here has a very special meaning in physics. Okay? These two things are kinetic energy. To measure kinetic energy, the kinetic energy an object has, it's 1/2 mv squared, 1/2 mass times velocity squared. So, for example, if we were to double an object's velocity, that would actually quadruple its kinetic energy. So it's kind of not really a nice one-to-one relationship there, but a very important relationship nonetheless. Now if we look at this, we have a v minus v naught squared, or 1/2 mv squared, 1/2 mv naught squared. Naught, remember, was usually standing for initial. So another way to think of this would be a change in kinetic energy. That it's kinetic energy final, over here, minus kinetic energy initial is the amount of work. So work can change the amount of kinetic energy an object has. In other words, applying a force on a system, shocker, causes motion, causes a change in velocity, causes us to change the amount of kinetic energy we had, right? Applying a force causes an acceleration. An acceleration is a change in velocity, so it should make good sense to us. So if we want to add kinetic energy to a system, if we want to get our system moving, we have to apply an external force and do work on that particular system to cause it to move.